Hey everyone, welcome back to the Weekly G. Recently, there's been a hurricane in the news. It's called Hurricane Sandy, and it has special significance to me because it actually stopped. I was traveling this weekend and the hurricane happened, so I actually couldn't fly back into Boston. So while I was stranded, I decided to look up how hurricanes work. So if you type that into Google, you'll get a bunch of pretty good articles and videos. So I combined a bunch of those to put this little video together. And kind of physicsed up the explanation a bit. But what I learned from reading all of these articles is that hurricanes are extremely complicated systems, which may have been obvious, but they're extremely complicated. So today I'm only going to be able to give you a very basic idea of what hurricanes are, and there's like millions of factors that I'm not talking about today. So what is a hurricane? To a physicist like me, a hurricane is a giant heat engine. And it's a heat engine that converts warm ocean water into strong circular winds. And some other details about it, there's an eye in the middle that is just kind of this region of calm air. So what does this mean? Well, let's draw a picture. So the first thing I said is that you need to start with some warm ocean water. Okay. So warm water. I think I read online that it's usually about 80 degrees Fahrenheit. No idea if that's actually true or not. And associated with this warm ocean water is kind of warm, wet air. And the reason it's warm is because the ocean water under it is also warm, and the reason it's wet is because you have a bunch of water evaporating from the ocean into the air. Okay, so you have this region of warm, wet air. Then up at the top, your cold reservoir is going to be this cool, dry air that is higher up in the atmosphere. Cool, dry air. Okay, and what a hurricane does is it brings the warm, wet air up to the cool, dry air. So I'm going to call this move air up. Okay? Then the next thing that happens is when this warm, wet air from down here, this red, warm, wet air, reaches the cool, dry air, then the water vapor inside of the air condenses. And when it does that, it releases something called latent heat. The inverse process of this happens when you're just boiling water on your stove. You're adding heat into water and into liquid water. And as you heat up the liquid water, some of it starts to evaporate, it starts to boil. And so this is the inverse process where you take water vapor and then you turn it back into liquid water. And then instead of absorbing energy, it actually releases energy. So the water condenses into clouds, and these things later make rain and stuff, but I'm going to ignore that for these purposes. But the important thing is that the water vapor condenses, releasing latent heat. Okay? And what this heat does is it actually heats up this cool, dry air. So you kind of get this this column of this ever-rising column of warm, wet air that is going up and up and up. Okay? And so essentially what I've described here is a mass transport of warm ocean water into the cool, dry air, which then kind of self-propagates itself, right? Because you have this column of warm, wet air, and it keeps going. So this is fine and dandy, but there's kind of two questions that you might be wondering about. So question A, how does warm, wet air get to the cool, dry air? Okay, so that's one question. The air starts down here, it has to get up there. How does it do that? The other question you might be wondering is, how does this make winds? Right? And especially, how does this make winds going in a circle? Okay? Both of these things can be answered by simple properties of gases. And the basic property that we're going to use today is that if you take a gas, heating gas, lowers the gas density, and it also lowers the gas pressure. Okay, so the answer to question A is pretty easy then. You probably have already guessed this, because when you start with warm, wet air down here, warm, wet air is less dense. And so less dense things rise, right? So, if you put oil in water, I think it rises or something like that. Every kid has done this experiment before. But when you have something that's less dense, it's going to rise. It's the same thing with air. When you have warmer, wet air, it's going to rise, and cooler, dry air is going to sink. Okay? So that explains how this water actually gets up from above the ocean up into the atmosphere where there's cool, dry air. And it's just because it's less dense, so it rises. Question B, how does this make winds? That's a little bit harder, but it's still not so bad. And so the question is, what is wind, right? Wind is essentially a flow of air from one place to another. And you can create a flow of air from one place to another if you have a difference in pressure between two places, right? So let's say I have a high pressure region, abbreviating pressure with P. You have a high pressure region over here, and you have a low pressure region over here. Then wind is going to go this way. Then the air is going to rush this way and create a wind. Okay? And so if you think about it, we have this column over here. This column over here of air that is warmer than its surroundings. And so that means that by this property that it has lower pressure. And so that means that air from the outside, where it is higher pressure, is going to rush towards this column of air. Okay, so let me draw a picture of this from a bird's eye view. So I'm going to draw it down here. So let's say that I have a bird. I'm looking from a bird's eye view or from a satellite or something. Let's say that this is my warm column of air. And then what happens is, I'll draw the winds in green. What's going to happen is your winds are going to be attracted this way, because this is a low pressure region, everywhere else is higher pressure, and so all the air is going to flow in towards this red dot. But there's something called the Coriolis force. And what the Coriolis force is it's a force that acts on things on the Earth because of the Earth's rotation. And I'm going to go into the details of this some other time, but what this ends up doing is it ends up actually, if you're in the northern hemisphere, it'll actually cause a force on the winds, and it's going to cause them to bend like this. Instead of just going straight towards the center, they're going to be deflected into this spiral. And then the resulting kind of, you can see this. If you add up all of those little purple things, you end up seeing that the wind is going to actually end up going around in a circle over here. If you do this in the southern hemisphere, it's actually going to go the other way because of the way cross products work. So yeah, that's actually essentially it. So what you do is you start with this. Let me just review this really quick. So you start with this column over here of warm, wet air. Because the air is warm, it is less dense, and so it rises up into the cool, dry atmosphere, and it kind of perpetuates itself because it's bringing all of this water vapor up into the atmosphere, up higher into the atmosphere, where the water then condenses into clouds. It releases latent heat, which keeps this column of air warm, right? Because otherwise it would not stay warm. You're moving hot things into a cold place. It's going to naturally cool down. But because it's constantly releasing the latent heat, this kind of continues to feed this column of air. And then what happens is, in addition to keeping it warm, or because it's warm, it is then also less. It has a lower pressure than the surrounding atmosphere, and what that does is then it creates, an airflow, which is just the wind, and the airflow is going to be towards this column. And then when you look down here, because of the Coriolis force, that's going to make these winds then spiral around each other, and that's what kind of makes the characteristic shape of the hurricane, this kind of circling thing. And you can imagine that in the center, you've heard about the eye of the hurricane. You can imagine in the center that at some point the force from the pressure balances with the Coriolis force to maintain this region where the winds just kind of can't get into. Cool. So that's how a hurricane works. I want to emphasize one thing that is of practical importance, which is that this hurricane engine relies on being fed by warm, wet water. The reason is that as soon as you stop, I kind of assume that this region over here would always have warm, wet water, which is always going to be rising, and then it's always going to be condensing and stuff over here. But once you bring it up over here, then it disappears. So how do you maintain this thing? Well, what ends up happening is because the air is rising over here, it also lowers the pressure in this region, and so it causes winds to blow in from up kind of like right at the ocean, and the air above the ocean is kind of moist, wet, and warm everywhere. So you bring in but you have to constantly be in a place that has lots of warm, wet air. Otherwise if you start feeding it like cool, dry air, if for some reason you move into like Antarctica or the Arctic Ocean or something like that where it's cold, you're going to start bringing in cold air, which is not really going to rise as much because it's more dense. So you have to constantly be feeding the hurricane with warm, wet water, which is fine if you're in the tropics. But what ends up happening is when you've probably heard that when you have a hurricane, it hits land, then the hurricane dissipates. And the reason is because obviously when you hit land, there's not a lot of water in the air above land, even if you're in the deep south and it's extremely humid. So there's definitely not as much air. There's not as much water in the air when you're above land, and so the hurricane stops being fed and it kind of starts to die. And so that's the reason a hurricane goes away when it hits land. Okay. Well, I think that's it for today. Thanks for listening, and see you next time.